Jack, 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 Jack. So, it was faster than expected. Uh, the fact that you released that. So, but I was in the middle of playing around with your code yesterday uh, on your blog. So I'm gonna put that aside for a second. I still want to go through that and get try to then replicate the graph, the sort of the graphs that you build in there as well from the Strawberry Fields interactive interface. But I think that deserves at least a sort of a read through, see if that brings any new knowledge to the thing. Okay, let me see. Can I just zoom in a bit? That looks good. So quick part 1 theory. That looks like a lot of stuff. That's good. VQE, QAOA, and then continuous variable. So there's a bit of theory. That can be nice because it might help me to connect the dots between all those three different things. And I don't know what to expect. I don't know if to expect anything in here in terms of a continuous variable. I don't think that I should expect a continuous variable quantum computing introduction in here at all, because I have to keep remembering I'm coming from the Yellow Submarine project from Michał, and I want to go back there eventually. And and at some point go back to discrete variable quantum computing as well. And I think I've done some interesting. I've come across some interesting analogies in terms of the beam splitting and how is the entanglement working there at an intuitive level, and then also I think when I was taking a look at the details of some of the gates, I don't know if it was the P gate or the Z gate. No, there was one of those gates where it was like it's similar to what the Hadamard is doing, right? Because of moving uncertainty around. What in continuous variable you call quadratures, so the position and the momentum, and in discrete variable quantum computing, you have your different computational bases, which sure you can have arbitrary ones, but you usually stick to the z, the x, and the y. And I see sort of a connection in there. But anyway, let's get to this. Fairly long bit of maths. Wow. Okay. I can hopefully. I don't hopefully have to go through each of the details, or I can kind of get an intuitive grasp of what those things are telling. Okay. Oh, wait a second. Simulating continuous variable QAOA for a simple problem. Okay, so that's the actual function of your blog post, of Jack's blog post. That here, and so that might be embedded in here, which is cool. Maybe rewritten, maybe. Yeah, look at this. The parabolic minimum, function optimize, the cost Hamiltonian, which is an S gate and a P gate. Wasn't there an R gate? No. Strawberry Fields. Gates. CV quantum computing. Wikipedia. I think there was a quantum is it not? Use quantum, no, continuous variable. Quantum computing. There's no proper strawberry field skates. I love these Google searches. Xanadu AI. Maybe there's a documentation. Anyway, I just wanted to have that open on the side. Interactive. So still, but I wanted the documentation. Algorithms. Settings. Software. Docs. Oh yeah, the sense animations. It's funny because this Xanadu thing feels like it's a hybrid. It's something in between annealing, like the quantum annealing from D-Wave, and the actual discrete variable quantum computing. But it's not. I mean, it's not really. It's closer to the discrete quantum variable computing. Gates. Come on. Come on. Why does this docs? API. Introduction. Here you've got the stuff. CV states. Squeezing skates and all that stuff. For unitary operations can be associated with a generating Hamiltonian. Gaussian gates, non-Gaussian gates. Yeah. Anyway, I think. Come on, Jack. Where's your blog? It's your blog. Yeah, this is your exactly. No, that's not. This is the post. Here, yeah, there's an R gate. Okay, so it is a bit different. Interesting. Okay, that's what I want to check. So the constant Hamiltonian is a bit different in the sense that there are it's only a Z gate and a P gate, and there's no an R gate. Because the R gates, those are the, this is the, yeah, this is the mixer, exactly. Here you've got the R gate. Yeah, but then here it's a bit, so here's even more. So here the mixer layer is an R gate, a P gate, and an R gate again. So this is what, so this is a bit more developed. Okay. Okay, but it seems. Oh, wait a second. Why is it is Fock and not Gaussian? And so the P gate, NAR gate. That's interesting. I thought that was supposed to be Gaussian, because aren't those all Gaussian gates? The non-Gaussian are beam splitter and cubic phase. The V and the BS gates. I love that it's called BS. Engine fog. So if I search for that, execution engine. This module implements the base engine. That's just the specification, I think. That's not what I'm interested in. Anyways, let me just go quickly through that. But that's the thing to note. So the fog engine, and here it was, if I search for engine on the page, a 1. But okay. I don't know what a 1 is. Maybe it's fog. Anyway, all the way. I don't know. For some reason, I thought it was Gaussian. Let's go ahead. Which I don't know exactly. The thing with the fog engine or the Gaussian engine, I don't know exactly the difference in here. I don't know if the fog engine is not basically to allow you to execute non-Gaussian gates. Alt circuit, run circuit, alt circuit. Why is it called alt circuit? Okay. But it seems to be a version of that post here. Okay, and then you've got like the cost and stuff. Okay, you've got okay, some of those things, and then what is this? Oh, cool. So that's seen from the top, I guess. Here's the full code, I guess, or I don't know. Quadratic function with 2 local minimums. Okay. So there's quite a lot of stuff, but I mean, I'm guessing that it's worth going through. I guess it's worth going through the theory part if I can. And then I wonder whether I just should go ahead with part 2, or I should go back to the blog post, because I was basically trying to play with these and try to recreate those plots, which was not working really well for me, and then go here, something like that. But I mean, that sounds like a good idea. So the goal is to provide the reader with a concrete understanding of q-qaoa over continuous variables to understand the physics that allow the algorithms to work properly, and to an explanation. Thanks, that's good. What is AQT? What is AQT? Alpine Quantum Technologies. I don't think that's what it is. Okay, with the variational principle, quantum mechanics, maybe. I don't know. Where was I? here, working out with theory behind CVQA, then in part 2 launching an actual concrete simulations. The first is this is the first version of this notebook because it's so long. I'm almost 100% sure there will be five mistakes. Okay, the variational quantum eigensolver. So before we jump into QAOA, I'm probably gonna try to kind of I'm gonna read through this, be quick, and stop where I see that I'm not really getting the detail. It's going to require a more general process. So the QA, okay, it is good to require a more general process, that of the variational quantum eigensolver. VQE is essentially a process that allows us to find the ground eigenvalue of some specified Hamiltonian by repeatedly guessing some quantum state that is parameterized by some parameters, calculating the expectation value of the Hamiltonian, then using a classical optimizer to update the parameters as this process is repeated until the algorithm converges on the... Yeah. So pick some set of parameters, generate some parameterized quantum state, that's your ansatz, I guess, using parameterized quantum gates, calculate this, which this is the expectation value, I think, yeah, which is nothing else than the average, right? Feed this value into a classical optimizer, which then generates a new set of parameters. Then go back to step 2, repeat the process until we have found the optimal state, I guess ground state, corresponding to the optimal energy. The reason the VQE works is because of an idea with quantum mechanics called the Variational Principle, which states that if I have some Hamiltonian describing a quantum system, and I choose some state vector, then this. Would I think what this means is the expectation value. That this is always going to be bigger or equal than the ground state. It seems trivial in the sense that the ground state is the lowest energy, so you shouldn't be able to find something that's lower than that. But where E is the ground state energy, the proof is fairly straightforward. Any vector can be expressed as a linear combination of energy eigenstates. Here you lost me for a second. Okay, let's just go ahead. So you expand that, and then you end up with these. It also follows that the minimum possible energy for this sum is when this equals 1 and the rest of the coefficients equals 0, because of the normalization condition. This is the ground state energy, so it follows that. This. Okay, that's in simple, but I'm not, as you already know, I'm not entirely I'm just reading those three things through. I really don't check whether this is something that makes sense. But intuitively, it's just I'm not super familiar with all the notation, especially the little star here. And this kind of assumption here, or this expression. Energy eigenstates. I guess eigenstates of the Hamiltonian. but the fact that you can express it this way, it's not entirely clear to me. But I'm not interested either. I think um, this is super cool. It basically means that if I have some Hamiltonian, I can pick any quantum state I want. The expectation value of the Hamiltonian corresponding to this state will always be greater than or equal to the ground state energy. Now let's say that I have some optimization problem which I must solve by minimizing some cost function. Well, if I can write this cost function as a Hamiltonian that acts on quantum states, then I can create a process in which I guess an initial wave function, calculate the expectation value, pass the result through initial classical optimizer, and continue to vary parameters of the initial wave function until I find the lowest energy state corresponding to E0. The variational principle tells me that I can never wrongly guess a wave function. Okay, so that's what I said. Like, you can't choose a wave function that corresponds to an extended energy below the ground state. This throwing off my optimization process. So you can't get it wrong. You can't get it that wrong. You can still be far off the energies, like, far off the actual optimal or the ground state, but you cannot get it wrong like past that ground state. The quantum approximation optimization algorithm. Okay, so these give me a second. Need to let that sink in for a second. So this has just been a quick overview on sort of the quantum mechanical background for these, which is this variational principle thing. It basically tells you you're allowed to. That works. In principle, that works. Now, I guess the trick here is how what is the state what is the answer you choose, so that you actually do get to some kind of minimum, or as close to E0 as possible. Quantum approximate optimization algorithm. I like to think of QAOA as a sort of a subclass of VQE. I'm lost with that already. People call it VQ's subclass of QAOA, whatever. No, actually, I think that was the last thing that I read was this one as well. So QAOA is not really. Specifically, I like to think QAOA as VQE, but with a particular ansatz strategy. Okay, yeah. That draws influence from quantum mechanics. When I say an ansatz strategy, I'm simply referring to the method used to prepare the parameterized state, which gates are used. For QAOA, we repeatedly apply our initial qubit state. For QAOA, we repeatedly apply to our initial qubit state the parameterized gate given by these. Okay. See, I haven't really read the original. I haven't really read the original QAOA paper in detail. But I thought when I read that introduction paper, I kind of got it wrong for some reason. I don't know. In the very beginning, when I was thinking, oh yeah, that's how you do this for the max cap problem, because I was like, yeah, you actually design the circuit in a way that it represents your problem. But that might have been the wrong thing to go through, because apparently the max cap problem doesn't need to follow specifically that. But okay, QAOA is sort of like it follows that specific pattern for the ansatz. HC is the cost Hamiltonian that we're trying to minimize, and HM is the non-commuting mixed Hamiltonian. So this is why you first, so you first apply a set of gates that basically are your cost function, and then the mixer, which we choose to expand our search space. It's an interesting way to see it. I think I have mentioned something similar in the past, but I'm not so sure that's straightforward to understand. That's the intuitive explanation. We'll see what the mixed Hamiltonian actually means soon. Okay. By using the gate sequence, the quantum state is recursively evolved to some state, corresponding to the optimal state for some Hamiltonian. The total evolution of the state through QAOA is given as this equals to the unitary applied to the state S which equals to, it's the product of a k of a set of unitary gates applied to S with its own parameters. And so these are values of your parameter set, and these are values of your alpha parameter set. Okay, for all k. Where these sets of parameters exactly used for our run for the algorithm. Okay, we're able to set the value. It's pretty early in the morning over here, sorry. I'm still having my coffee. We're able to set the value of k with k approaching infinite, theoretically leading to I guess to the grounds, okay, to zero. However, typo here. This is not the case in reality, as increasing circuit depth increases error. Okay, yeah. So it is up to the individual utilizing the algorithm to turn the knobs to set k to a value that gives error below a desired threshold, while also keeping in mind quantum hardware limitations and noise. Since this is a variational algorithm, a classical optimizer will optimize our angles, our parameters, angles, that's just parameters, over repeated runs of the circuit until we converge on parameters that. So I remember this kind of, I kind of had a bit of a flashback when I first read the, when I would first check the yellow submarine project, and I was like, what the hell, what are those angles? Why are you now, what are those angles? I was like, what is that? Just the concept of parameterizing the circuit was a bit weird. Now it feels just natural. Until we converge on parameters that yield a state which, when measured, yields the lowest value of the cost function. You may wonder, maybe wondering now why cv-qaoa actually makes sense as an ansatz strategy. Basically, well, yeah, actually, it's good that you say that. Basically, we have some cost function that we want to minimize, which we express as a Hamiltonian acting on a quantum state vector, vectors called HC. Well, there's no guarantee that our Hamiltonian is unitary and can thus represent a quantum gate operation. However, it is true that an operator of the form like that is unitary. In fact, recall from quantum mechanics the time-dependent Schrödinger equation. Yeah. Well, we also have these expanding in these bases yields uncoupled differential equations describing the components, which we then solve to get the general time dependence of energy eigenstates. But we also have these, putting all this together, we have these. I'm just skipping through that. So since the En states from a complete basis, we have these. I might come back to that, see if that's understandable, but I wanna skip that for now. We can exploit this, but we first have to deal with the exponential. It turns out, blah blah, which we can easily show. So we have a unitary called U, which we can call the time evolution operator, as it performs the transformation from time 0 to time t. Well, this looks awfully similar to the parameterized unitaries that we use for cv-qaoa. This is no coincidence. The idea with cv-qaoa is that we evolve our state in time to the ground state of our cost Hamiltonian. Okay. In order for this idea to fully make sense, we need to discuss quantum adiabatic evolution. Consider the Hamiltonian that evolves in time due to some continuously applied perturbation. The idea is that if we have some quantum system that starts at t equals 0, and the ground state of some Mixa Hamiltonian, in the ground state of some mixed Hamiltonian. Why is the mixed Hamiltonian coming in here right now? Whatever. And we slowly evolve the Hamiltonian over time. Then the evolution of our quantum state will tend towards the ground state of the new cos Hamiltonian. This is formally known as the quantum adiabatic theorem. Okay, the parameter t allows us to control. That's why this adiabatic quantum computing. Well, that's why they say QAA is inspired on adiabatic quantum computing. Actually, because I saw this, I read this somewhere, but I was like, how? Okay, this is formally known as the quantum adiabatic theorem. The parameter t allows us to control how quickly we evolve from hm to hc. Theoretically, as t approaches infinite, our state approaches the ground state with probability 1. For QAA, we're basically utilizing the discrete version of this process. So we start with a qubit in a ground state, which we call M0. Now things are going to get hairy. Time evolution according to as time-dependent Hamiltonian is different than time-independent one. We must use something called the Dyson series, which I won't go into this article in this article to arrive at the fact that between T1 and T2, the time evolution operator is this thing here. Let's compute this integral and see what happens. We're evolving our quantum system from T0 to Tt. Since we're not dealing with I need to realize this operator quantum circuit. Oh, again this word. I think I once attempted to understand what this means, but in order to realize this operator in a quantum circuit, we have to trotterize it. When I say trotterize, I mean we have to perform a Trotter-Suzuki decomposition. Okay, which says that. Okay, where the approximation gets better as g increases. This equates to an increased number of steps in our algorithm. The applications of the parameterized unitary. From this we have. Oh man, that is heavy. Now we have a nice ansatz that should solve our quantum state to the ground state of Hc. However, where do the parameters alpha and this come into play? Since the Trotter-Suzuki decomposition is not exact. The exact form of the expansion of the. I mean, it's not that I understand that, but it intuitively makes sense because you're. So at some point you're making some sort of like, that's not an equality. It's not equal, but it's roughly equal. So adding the parameters allows you to kind of play with that. Okay, the exact form of the expansion of the exponential is given by the Baker-Campbell-Hausdorff formula, which is an infinite product of commutators of the operators in the exponential, and we are limited to a finite value of g. Actually, g has to be pretty small to keep circuit depth low. In addition, we can't always initialize our system in the ground state with a mixed Hamiltonian, as often strategies are utilized where the mix's purpose is to search the space of feasible solutions or encode hard constraints. In these cases, the initial state is often set to overlap many possible states. Exactly. So like a superposition, right? That they obey the hard constraints. This means that we need to introduce another degree or degrees of freedom to our state preparation circuit in order to get acceptable results. Thus we parameterize our exponential operators with this. That's interesting. That's actually that's actually an interest. It's good to know. That's you kind of think about it like without all the detail. You more or less know that you're doing that to explore a bit the space, but the actual reason is really it's really kind of connected to the mathematics behind this. The final evolution of our state after applying QAOA is given by this. So if we've done everything correct, we should get a state that is approximately the ground state of our cos Hamiltonian, which is exactly the problem we're attempting to solve. And then we got CVQAOA. Okay, but before we dive into this, let's just let that sink in for a bit. I mean, I'm not done yet. So now consider what happens when we take a measurement of the quantum state we have prepared, which you should recall is denoted this. Now that we have prepared our quantum state as one does in a variational, so to this we sample the circuit repeatedly, measuring the basis of energy eigenstates. In most cases, for discrete QAOA, we express our cos function. We express our cos function with Pauli Z operators. So this ends up being the standard computational basis. In CVQAOA, we will soon show that our cos functions are expressed in terms of x operations, so of the position operations. So we take an x homodyne measurement. Okay. Now, for measurement, we obtain a result k, and then we feed the value associated with k, which we will call k, into our classical cos function. And after many samples, take the average of the sum of all outputs of the cos function is the sample circuit n times, then we get the quantity, the amount of times I is measured. So we have proven that our method of calculating the cos function is valid, as the quantity that calculates by sampling our circuit is equivalent to this. The same kind of logic applies to continuous spectra of energy, but we are approximating the integral over all possible values with the Riemann sum, whatever that means. Okay, let that sink in, because there's a lot of useful information in here, and I have to admit that I haven't. It's a pretty nice way to put it. It's sort of another angle, and that it definitely helps a lot to read this, because you read bits and pieces from different places, and it kind of helps you give the full picture. And that's something you will never get if you just go through one course, or you just read one book, or that's super helpful. Okay, let's recap a bit. So let's recap a bit. VQE, yeah. So that we read here, the QAOA, right? So the idea here is that what Jack is saying here is basically QAOA is VQE, but following that particular strategy. And so the rest of that concrete chapter goes ahead trying to explain where does this come from, right? And so still how then this gets translated into a discrete quantum computing circuit, it's another story, right? But because here, when Jack talks about how to transform that into a CV quantum computing circuit, he just goes and he's like, oh yeah, we've got those operations which basically actually can be expressed in a really similar way. So you just, that's it, right? Mathematically straightforward, but intuitively there's no, there's something, I feel there's something that it's missing for me, at least. Whereas in the discrete version, I think it's like basically what you're saying is you've got your cost function, you've got the mixer, the cost function, the mixer part. So you apply first the cost, then the mixer, right? That's the concept. But all this is telling you is, it's just making it so that it's forcing for this to be unitary, because it has to be something you can put into a quantum circuit. But then that doesn't tell you like how to, what kind of gates to use and how to use them. So that really depends on your Hamiltonian. That's just something that in a compact way just allows you to run the maths, because basically what then Jack goes ahead and shows here is that the reason this is this is derived from the fact that there's this adiabatic principle or whatever that says that if you've got a Hamiltonian and you let it evolve through time, it will eventually get to the ground state. It seems to be sort of that same as in classical physics, is this kind of is it called the principle of the conservation of energy or something like that? I don't know exactly what it is, but it's like this idea that everything tends to, like, if there's no sort of active influence or external influence, all physical systems tend to go from an excited state to like a ground state where they where there's no energy going around. It seems to be something along the same lines, but at the quantum level. And so what Jack goes ahead and does here is a proof that I really can't follow. I really am not able to follow it. Right? Not sure whether it's really so key, but I mean to understand that. But it's like basically, and he's just mixing the Schrodinger's equation at some point. The time-dependent Schrodinger's equation. And out of all these, you get to the point where so he is trying to basically what he's trying to figure out is, okay, so how do we mathematically represent the needed steps to get you from like the Hamiltonian at time 0 and then at another time t, right? In theory, if that t approaches infinite, then this means you're kind of waiting forever. Then it means that takes you ideally to the pure ground state. But you don't need to you don't need to approach infinite to get close enough to the ground state. And so he's plugging in all those equations to basically try to find out what are the things that need to happen in between. And then that basically leads you somehow to that. So I think that's just here. Just Jack is here just talking about like the just proving that that sampling works. That the expectation value, the average thing, then gives you the right approximation. This is it. So explains where the parameters are coming from and why there are parameters, which is intuitively because if you want to explore the space, but but really at the technical level, this is because in order to get there, you're doing this structurization in here, which is not a concrete thing. So you want to you want to allow you want to introduce some degrees of freedom in here. Yeah, I think I'm not sure I fully get it. So I might really kind of go through that again. But I think I get the gist of it. I mean, definitely I'm not going to understand I'm not going to spend time trying to understand the maths at a super technical level. But that's I think what Jack's trying to do here is basically trying to prove where is this coming from and why is it correct, so to say. Okay. But now the question of how you translate that into a circuit, it's something that is not definitely covered in here, right? And then, but the concept of you've got a cost function and then you've got the mixer function. And now let's see. It's gonna be a pretty long video, I think, but let me see if I can because this continuous variable QA and QANA. Okay, and then we're ready to get into the simulation stuff, like creating quadrature plots and then simulating things. So I don't want to rush it either. But let me scan it through, see if there's anything new in here for me that is important. And then, so this is going to be the coolest section of the notebook, in my opinion, because despite being short, we'll get some more intuition as to why the continuous variable analog actually works. Of course, the method that we outlined in the previous section generalizes well to the continuous or discrete QDID model. However, the introduction in the paper provides an even more intuition as to why this method works. In order to create a QAOA over continuous variables, we follow the same process of creating a mixer and a cost Hamiltonian. For the cost unitary, we will initialize our cost Hamiltonian. The unitary is given by the imaginary exponential by creating a function with respect to the position quadrature, which is just the observable operator that corresponds to position. Well, not actually position. A QMO doesn't actually move around like a particle in some potential, but it behaves pretty much identical to how the position operator behaves when acted upon by operators of the In reality, the two quadratures that we use in photonic quantum computing represent in-phase and out-of-phase components of an electric field. Anyways, if we have some scalar function, we will transform it as this. Okay, for example. Where fx is the actual cost function that we're trying to minimize. Okay, so you're basically transforming the x into the, meaning that's the position quadrature. In order to implement continuous variable quantum QAOA, we follow the same general process. Choose a cost mixer Hamiltonian, which we then trotterize and recursively act upon our photonic modes. The unitary for our mixer we're required to define our mixer Hamiltonian. Let's first consider a mixer which we will call the kinetic mixer, defined by the Hamiltonian, and thus the unitary, okay, kinetic mixer, where the sum over all modes is implied in the exponential. Consider how an application of this gate transforms our position operator I feel I'm gonna rush this. I don't want to rush this. What is he trying to prove here, though? Then there's another mixer, the number mixer. Where are those mixes coming from? Adiabatic theorem. So up to an overall phase, our number mixer corresponds to the time evolution of a state in the quantum harmonic oscillator potential, which again helps to expand our search space. What is he trying to... Jack, what are you trying to explain here? This is a starkly elegant interpretation of the QAOA ansatz over continuous variables. With our classical optimizer, we have to find the amount of time which we must evolve our system, which we can then visualize as the particle traveling around in a potential landscape, such that it ends up in position with that minimizes potential energy. It's the same procedure as gradient descent. We're choosing parameters such that our particle ends up at the bottom of a potential landscape, where it evolves in the direction of the negative gradient. From the physical perspective, it is being acted upon by some force and thus tends towards the position where the force is pointing. Point of equilibrium. Now let's consider another mixer. So, but this is just, okay, so okay, first, I think I'm rushing this too much, so I'm gonna stop here and do another video on this, definitely. Second, I'm not entirely sure what's the goal of that section, other than saying, okay, with cv-qaoa we basically use the position quadrature, but I'm not so sure why we can't. Why can't we use why can't we use the um, momentum quadrature, the p quadrature? I mean, maybe that's what he's trying to prove here by talking through different mixers and proving that those mixers actually do what they're supposed to do, which is take us to the actual ground state. Okay. Mhm. Then creating quadrature plots with strawberry fields. With the Winger function, which is 3D graph phase space. Each point analogs to the quantum mechanical probability density tells us the probability of measuring a particle's x and p quadrature values between x and blah, 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 blah. Okay, so this is already then getting the hands on with the actual simulation. And this is the same thing as the blog post. So maybe I'll try to let that sink in for a bit. So I'll do the following. So in my next video, I'll probably come back to the blog post, try to figure out those plots. Then I'll go here and maybe do a quick reread of the cv-qaoa part again. But I want to give it the right attention, so I don't want to rush it. And as I'm running out of time for today's video, yeah, it's not good. But I think I got some fairly big amount of connections here and there between different things that I had read before for the theory part. That's nice, cool. And then there's a bunch of simulations. Okay, for a simple problem, a harder problem. Curious what the harder problem is. Like a question involving two variables. Ah, okay. Interesting. So you got it. Fancier things in here. Okay. Cool. Yeah. Pretty helpful. It's really cool that all this material is available. And as I said, so once I get that straight, then the plots, then back to these, then maybe go through that. But I really eventually want to go back to the yellow Submarine project. And I think I'm gonna end up. I don't know if I'm because those are two different projects. I'm kind of going from one place to another, mixing things up, and I don't know if I'm gonna then organize the videos in a bit of a different way. In hindsight, but I mean it's fine. Yeah, I think I'll have spent enough time on these, and then I'll probably, after the whole yellow Submarine thing, will be then time to actually go and pick another project that it's more on the discrete side of quantum computing, which to some extent I miss as well. Perfect, cool, good stuff.